First of all, I'd like to thank the organizers for invitation here. Not working? Yeah. So today I'd like to talk about our recent result on the steady state of the macroscopic open quantum systems in the weak dissipation regime. And my collaborator is Tatsuhiko Shirai. Okay. In this talk, I'd like to discuss a connection between the eigenstate thermalization hypothesis and the non-equilibrium steady state in the open system. ETH ensures that the system relaxes to a thermal equilibrium state that is described by the Gibbs ensemble when the system is completely isolated from the environment. But in my talk, I'd like to discuss a situation in which the system is weakly coupled to the surrounding environment. And in particular, I'm interested in the situation in which the environment is out of equilibrium. So yeah, I'm interested in the steady state and the dissipation into the non-equilibrium environment. So I'll show you that even in this case, the ETH still plays an important role in characterizing the NESS of this kind of open system. Okay, this is the outline of my talk. So first, I start from the introduction of the Lindblad equation in driven-dissipative systems, and then I develop the weak dissipation perturbation theory for NESS, and it will be argued that the NESS is well described by a thermal Gibbs state. So this is a consequence of the perturbation theory and the ETH. But the problem is that the validity of the perturbation theory is non-trivial, especially in the macroscopic systems. So next, I discuss this problem, and I explain our result on the criterion for validity of the perturbation theory beyond its convergence radius. And finally, I show you some numerical results, and it is found that they are consistent with our theory. So yeah, let me start with the introduction. So let us consider a system in contact with a large environment. Then the Hamiltonian of the total system consists of the three parts. The HS is the Hamiltonian of the system of interest, and HE is the Hamiltonian of the environment, and this is the interaction. And I discuss the dynamics of the reduced density matrix of the system of interest given here. And it is known that the completely positive Markovian time evolution is generally described by the Lindblad mass equation given here. Okay, in this right-hand side, this term represents a unitary time evolution under the system Hamiltonian. And this part represents the effect of dissipation. Okay? And this LA characterizes the type of dissipation, and it is called the Lindblad operator. Okay, in my talk, I discuss a problem in the two different settings. In the first setting, I consider a lattice system, okay? And each lattice site is coupled to the environment in this way. So in this case, the dissipation is present in the bulk, so I call it the bulk dissipation. This setting pays much attention recently because recent experiments using the ultra-cold atoms or trapped ions now enable us to control the dissipation, bulk dissipation. And by doing that, we can induce some non-equilibrium phase transitions. Yeah, and I'm also interested in the situation in which the dissipation acts only at the edge of the system in this way. So I call it the boundary dissipation. Yeah, of course, it is a central problem of non-equilibrium statistical physics to understand the transport properties under the boundary dissipation with different temperature or different chemical potentials. Okay, I consider these situations. Okay, first, I mention about the microscopic derivation of the Lindblad equation. The Lindblad equation is familiarly used in analyzing the open systems, but its microscopic derivation is not so trivial, especially for the macroscopic systems. So in the usual derivation of the Lindblad equation, we often assume the weak interaction limit between the system and the environment, and the so-called rotating wave approximation or the secular approximation is used to derive the Lindblad equation. But strictly speaking, this approximation is justified only when the gamma is the strength of the dissipation here. This gamma is much smaller than the energy spacing of the system Hamiltonian. So if we consider a macroscopic system, this is exponentially small in the volume of the system. So this condition cannot be satisfied in macroscopic systems. So I consider a different derivation. So in another familiar derivation, it is assumed that the dynamics of the environment is very fast. So the correlation time of the environment can be regarded as infinitesimal. So if we assume it, then we can derive the Lindblad mass equation. So in order to explain this, let us consider the interaction Hamiltonian of the simple form. Here, X is an operator acting to the system, and Y is an operator to the environment. Then define the Bass correlation function in this way, and its Fourier transform is denoted by eta of omega. Then, if this phi t is approximated by the delta function or equivalently, this eta of omega is approximately constant, then one can derive the Lindblad master equation. But okay, yeah, this derivation also has a problem when the environment is in thermal equilibrium. So in this case, this eta of omega must satisfy the so-called Kubo-Martin-Schwinger relation that is given here. So except for the high temperature limit or the classical limit, eta of omega cannot be constant. So in this way, the microscopic derivation of the Lindblad equation for macroscopic quantum systems in contact with an equilibrium bus is not so trivial. But here I point out that if we go to the out of equilibrium situation, for example, if we consider the non-equilibrium bus, then there is no Kubo-Martin-Schwinger relation. So the environment may have the infinitesimal correlation time. So we may be able to derive the Lindblad equation along this second approach. And it is indeed true for several driven-dissipative systems. Okay, as a specific example, let us consider the laser-driven Dewdrey atoms on the one-dimensional lattice. The Hamiltonian is given here, and each atom is regarded as a two-level system. So yeah, this is expressed by the spin 1/2 operator. The up spin corresponds to the excited state, and the down spin corresponds to the ground state of the atom. So this term represents the nearest neighbor interaction between Dewdrey atoms, and this epsilon is an excited energy, and this final term represents the laser driving. So it depends on time explicitly. And here I consider the bulk dissipation. So I assume that each atom is in contact with its own environment independently in this way. So I assume that the environment is modeled by the equilibrium boson bus. The Hamiltonian is given here. Okay, so this system is out of equilibrium because of the presence of this laser driving field. But in this model, this time dependence can be completely eliminated by moving to the rotating frame. The rotating frame, these operators are oscillating in time with the same frequency as the laser driving. So, and in this case, the Hamiltonian is transformed like this. Okay? This time dependence disappears, so this is just a static transverse field. But instead, this epsilon is shifted by capital omega. That is the frequency of the laser driving. And similarly, the energy of bosons in environment is also shifted by capital omega. And because of this frequency shift, the environment is no longer in thermal equilibrium in the rotating frame. So we have a static system in contact with a non-equilibrium environment. Indeed, if we consider the Bass correlation function and its Fourier transform, then this eta is transformed into eta tilde in the rotating frame, and it is related to the original eta in this way. So yeah, original eta satisfies the Kubo-Martin-Schwinger relation, but this eta tilde does not. And when this frequency omega is much greater than any other relevant energy scale in the rotating frame, then this small omega can be neglected. So this is just a constant. The constant eta implies the infinitesimal correlation time, so we can derive the Lindblad equation. So in this way, the Lindblad equation for macroscopic systems is relevant for this kind of driven-dissipative systems. Okay, so this is a derived Lindblad equation for the Dewdrey system. So this second term represents a dissipative transition from the excited state to the ground state. And this part represents a transition from the ground state to the excited state. And the ratio of the strength of these two processes satisfies this equality. The beta E is the inverse temperature of the environment in the static frame. Okay, this looks like a detailed balance condition, but it is not the case. This capital omega is just a frequency of the laser driving, so it is nothing to do with the energy gain or energy loss in these dissipative processes. And because of the lack of the detailed balance condition, the non-equilibrium steady state of this master equation is non-trivial. So I'd like to investigate the NESS of this kind of Lindblad master equation for driven-dissipative systems. Okay, and this problem is partially motivated by recent experimental attempts to control or even design the dissipation so that the NESS has a desirable property. But yeah, of course, it is a long-standing fundamental problem to understand the steady state of many-body open systems in such a non-equilibrium situation. Okay, so now I consider the non-equilibrium steady state. So first, I try to obtain the density matrix of the NESS by considering the perturbation theory. Okay, and the steady state density matrix satisfies this equation. So now we expand the density matrix in terms of gamma in this way. Then the perturbative solution is obtained by solving this equation order by order. So in the leading order term, the equation is given here. So this means that the rho 0 is a diagonal matrix in the energy basis. But the distribution Pn is not determined in the leading order term. So I go to the next leading order term. So this equation contains both rho 0 and rho 1. But if I focus on the diagonal element of this equation, then this first term disappears. So I have a condition for rho 0. So by substituting the definition of the dissipator D is given here. So then I have the set of equations for Pn. So by solving these equations, I can get Pn. So we can determine the rho 0 completely. Yeah, this W and M is defined by the Lindblad operator in this way. And this is interpreted as a transition rate from the state M to the state N. So this equation is interpreted as some kind of balance equation in the classical master equation. Okay, and I emphasize that these transition rates do not satisfy the detailed balance condition. Okay, yeah, it is actually due to the non-equilibrium nature of the environment. Anyway, we can obtain the perturbative solution order by order in this way. And it is expected that for small gamma, the exact density matrix is approximated by the leading order perturbation solution. So it means that the steady state is described by a diagonal density matrix in the energy basis. So here, the eigenstate thermalization hypothesis plays a crucial role. The statement of the ETH is that the matrix element of a local operator is written in this form. Okay? And here, this one is an equilibrium value of the local operator. So this first term implies that the diagonal element is a smooth function of the energy, and it also means that the individual energy eigenstate looks thermal. And this property is called the diagonal ETH. On the other hand, the second, this term characterizes the off-diagonal element of the local operator. And here, this D is the dimension of the energy shell, so it is exponentially large in the volume of the system. So this part implies that any off-diagonal matrix element is exponentially small. Next, this R and M looks like a random variable. So this part implies that off-diagonal matrix elements are randomly fluctuating. And finally, this function FO is a smooth function of its arguments. So, and it decays exponentially for large energy difference, omega nm. Okay, and this behavior of the off-diagonal matrix element is called the off-diagonal ETH. And it is believed that the ETH is satisfied for a wide class of non-integrable systems. So I assume that our system Hamiltonian satisfies the ETH. Okay, so now I go back to the discussion of NESS. So according to the ETH, as long as the energy fluctuation is sub-extensive, then any diagonal density matrix is indistinguishable from a thermal Gibbs state. So it means that, okay, by combining this conclusion with the result of the perturbation theory, the NESS is locally equivalent to a Gibbs state at a certain effective temperature. This is a simple but important observation. Okay, so now I explain how to determine the effective temperature in the steady state. So in principle, the effective temperature is determined by comparing the energy in the Gibbs state and that in the leading order perturbation solution. So this is a direct estimation of beta, but it is not so convenient practically because it is very difficult to, numerically hard to get rho 0. In order to get rho 0, we have to solve these equations. But this transition rate is defined by the matrix element of the Lindblad operator. So in order to get this one, we have to perform the exact diagonalization. So it is a numerically hard task. So instead, I propose a different method to determine beta. So, and yeah, beta is determined by the following condition. So yeah, the expectation value of the energy does not change with time if we start from a Gibbs state at a proper effective temperature. This is a necessary condition of the steady state. And okay, this condition is equivalent to this one. So by solving this equation, we can get beta. Yeah, and it is much easier to solve this equation compared to this one, because C of beta defined here is just an equilibrium quantity, okay? The equilibrium average of this object. So I can compute C of beta by using some equilibrium algorithm, like the quantum Monte Carlo method or something. Anyway, beta is determined by solving this equation. Okay, and as an important consequence of C of beta, one can show that it is non-negative at plus infinity and it is non-positive at minus infinity. So this property ensures that there exists at least one solution of this equation. Okay, the proof of this inequality is very simple. So we consider the case of beta equal infinity. In this case, C of beta is written by the ground state expectation value of this object. So now I decompose the commutator into the two parts. Okay? And then this is written in this form. Here, the state phi is defined here. So, and the expectation value of the energy must be greater than or equal to the ground state energy. So this is non-negative. Okay, similarly, one can show this inequality. And okay, so this is a typical profile of C of beta as a function of beta. This is calculated for a specific model, specific spin chain model. And in this case, the C of beta crosses at 0 at around 0.25. So in this way, we can determine beta. Okay, in this way, if we consider the perturbation theory and the ETH, then it is concluded that the NESS is described by a thermal Gibbs state. The argument is quite general, but maybe you feel that the argument is too general. So actually, one cannot believe this conclusion immediately. So actually, there is a problem in the argument. Okay, I have considered the expansion of the density matrix in powers of gamma in this way, but it is known that this expansion has a convergence radius exponentially shrinking in the thermodynamic limit. So it means that it is a non-trivial problem whether the exact density matrix is rarely approximated by the perturbative solution, even for very small gamma in the thermodynamic limit. So the purpose of our work is to clarify what happens beyond the convergence radius. Okay, so in order to answer this problem, we derived the criterion for the validity of the perturbation theory. The result is given here. Okay, this beta is the effective temperature in the steady state, and this delta is related to the gap of the Liouvillien in this way. Okay, gap is defined by gamma delta, and that is the smallest non-zero absolute value among all the eigenvalues of the Liouvillien. Okay. And here, this V is the number of lattice sites in the system. So this is the dimensionless volume of the system. And this Vd is the number of Lindblad operators appearing in the equation. So in the case of bulk dissipation, Vd is proportional to V, while in the boundary dissipation, it is proportional to the surface area of the system. Okay, so yeah, this is our criterion, but I emphasize that this is not rigorous at all. So we obtained this criterion just heuristically. So now I explain our heuristic derivation of this result. Okay, so now I decompose the exact density matrix into the two parts. Okay, this is the leading order perturbation solution, and this is the deviation. And then the steady state density matrix satisfies this equation. So I substitute this one into here. Then I get this one. Yeah, and here in this second equality, I use the fact that the rho 0 is a diagonal matrix in the energy basis. So this part disappears. So I have the second equality. Then by introducing the pseudo inverse of the Liouville operator, then delta rho is formally expressed in this way. So yeah, this is just a formal expression, but I want to evaluate the order of magnitude of delta rho. Okay, so I start from this part, d rho 0. Okay, d rho 0 is given here. Okay, I want to evaluate this one. So in order to evaluate it, I introduce the energy shell around the mean energy in the steady state. And okay, so I denote D by D denotes the dimension of the energy shell. Then the diagonal element of rho 0 is roughly proportional to 1 over D, while the off-diagonal matrix element of the Lindblad operator is proportional to 1 over square root of D, according to the off-diagonal ETH. Okay? By using them, I get the rough estimate of D rho 0 this way. It is proportional to the square root of Vd, and it is inversely proportional to d to the 3 over 2. And this square root dependence comes from the fact that the off-diagonal matrix elements of the Lindblad operator behave randomly. The summation of the random variables leads to the square root dependence on the number of random variables. So therefore, I get this kind of square root dependence here and here. And here, this summation is restricted by the cutoff frequency lambda. And this is introduced because the off-diagonal matrix element decays exponentially for large energy difference. This strict cutoff is just for simplicity, so it is not essential. Okay, so now I next consider the multiplication of the pseudo inverse of the Liouvillien. here it is expected that the dominant contribution comes from the small eigenvalues of the Liouvillean because this is the inverse of L. And so I focus on the contribution near the coming from the gap of the Liouvillean gamma delta. And okay, so the small eigenvalues of the Liouvillean correspond to the slowly decay mode of the dynamics, and it is expected that the such slow mode would be constituted from the low frequency matrix element with the energy difference not greater than the gap of the Liouvillean gamma delta. This is just an assumption. Okay, so in other words, the first oscillation in the system dynamics is not relevant for the slowly decay mode of the Liouvillean. I think it is natural, and indeed numerics verify this property, so I assume it. Okay, because of this assumption, the delta rho is finally evaluated in this way. Here, this denominator, the delta in the denominator appears because of the pseudo inverse of L. And here now, this summation is restricted by the gap of the Liouvillean because of this assumption. Okay, this is a final estimate of delta rho. So by using this, I evaluate the expectation value of the macroscopic quantity. The macroscopic quantity is defined by the translational sum of the local operators, translationally invariant sum of the local operators in this way. And here, M prime is defined by putting all the diagonal elements of M to 0. Okay, then I compare the expectation value of M in the exact steady state and that in the leading order perturbation solution. Then, okay, by using the diagonal ETH, the diagonal element of this does not matter. So M can be replaced by M prime. And then this is just a delta rho. And by using the Schwarz inequality, I get this upper bound using the Frobenius norm of M prime and delta rho. Okay, and we can evaluate the Frobenius norm of delta rho by using the rough estimate of delta rho in the previous slide. I do not explain the detail, but the final result is given here. And okay, on the other hand, the Frobenius norm of M prime is also evaluated by using the off-diagonal ETH. Okay, the result is here. So by using these estimates, okay, this upper bound is roughly given in this way. So yeah, this means that if this quantity is very small, then the exact density matrix is indistinguishable from the leading order perturbation solution, as far as macroscopic quantities are concerned. Okay, so yeah, in this way, I get this criterion. Okay, now I explain the consequence of this criterion. First, I consider the case of bulk dissipation. In this case, our criterion suggests that the perturbation theory works if the beta gamma is much smaller than the scaled gap delta. And okay, for many specific models, the numerical simulation for specific models, it is known that actually the Liouvillean is gapped in the sense that the thermodynamic limit followed by the weak dissipation limit of delta is strictly positive. Okay? So in this sense, it is gapped. So yeah, this result implies that this condition can be satisfied for sufficiently small gamma even in the thermodynamic limit. So yeah, it means that the NESS is well described by a Gibbs state for sufficiently small gamma in the thermodynamic limit, although the convergence radius is 0. This is our main conclusion. Next, I consider the case of the boundary dissipation. In this case, our criterion suggests that the perturbation theory works if the beta gamma is much smaller than L delta. The L is the linear dimension of the system, or yeah, the length of the system. And in this case, okay, as for the gap of the Liouvillean in the boundary dissipative systems, the Znidalik, in the previous work by Znidalik, reported that in many cases, this delta scales as L to the minus theta with the exponent theta greater than or equal to 1. And in many cases, the theta is strictly greater than 1. And in this case, our criterion suggests that the NESS is not described by a Gibbs state for arbitrary gamma in the thermodynamic limit. Okay, so this is a consequence of our criterion. Yes.
One question about the terminology. I mean, you're saying NESS is Gibbs for sufficiently small. I mean, that's fine. But do you mean Gibbs relative to your Hamiltonian, or could it be some other Hamiltonian?
Gibbs for, yes, the system Hamiltonian, our Hamiltonian.
But I mean, wouldn't it be a more reasonable conjecture that it's Gibbs for some other Hamiltonian? Or why should it be for the same one?
Yeah, Gibbs for the same.
It could be some e to the minus beta of some other Hamiltonian, short-range Hamiltonian. I mean, we should sort of equally interesting and valid.
Okay, I consider the Gibbs with respect to the system Hamiltonian.
I didn't.
Question is why? I mean, you put this, sort of interaction with this environment, and then what you're trying to say is that it might look very similar to the Gibbs state, of course, some other Hamiltonian.
Okay. Yeah.
What is so special about your initial?
Because we consider the regime of the weak dissipation. So if we consider the perturbation theory, for example, in the reading of the perturbation theory, the steady state is described by a diagonal density matrix in the original Hamiltonian, system Hamiltonian.
The lowest order solution is steady state for this W.
Yeah.
And you argue that it's given by the Gibbs.
But
like one.
But if we believe the ETH, then any diagonal matrix is indistinguishable from the Gibbs state of the system Hamiltonian, even though the detailed balance condition is violated. This is the point. So yeah, actually, if we believe the strong ETH, then any diagonal density matrix is indistinguishable from the Gibbs state.
Constant like a difference. But you're saying that this given a solution to.
Yes. Oh, yeah. Sorry. The density matrix itself is not the same as the Gibbs one. Sorry, but if we consider the expectation value over macroscopic quantity, then it is indistinguishable from the Gibbs ensemble with respect to the system Hamiltonian. Density matrix is different, but the expectation value over local quantity is the same. Yes, sorry. Okay, so yeah, this is a result, our result. So now I'd like to discuss numerical results. So in numerics, I consider I calculate the relative entropy density of the two states, the exact density matrix and the rho zero. And here, it is known that if the relative entropy density vanishes in the thermodynamic limit, then the two states rho and rho prime are macroscopically equivalent. So yeah, more precisely, it is known that if we consider the difference between the expectation value of the macroscopic quantity in the two states, then it is roughly bounded by square root of the relative entropy density. And okay, as for this part, we have already obtained the behavior in this way. So this inequality indicates that the relative entropy density behaves like this. It is our estimation of the relative entropy density. Anyway, by computing the relative entropy density, we can judge whether the perturbation theory works or not. Okay, so now I start from the model of the bulk dissipation. Okay, in this model, I consider the spin 1/2 chain. Okay, and this model is equivalent to the one of the Dewdrey atoms, as I explained in introduction. And this model is known to be non-integrable and ETH holds. So now as a dissipator, I consider the transition from the upspin to the downspin. Then our criterion is given here. And if we compute the gap of the Liouvillean for this model numerically, then I find that it is strictly positive in this limit. So it is above 1.5. So we expect that in this case, the perturbation theory works very small gamma, even in the thermodynamic limit. Okay, so this is our numerical result for the relative entropy density. So first, I calculate it for several small gamma. So this is a system size dependence of the relative entropy density. So this is a 1/v. So you find that it shows a linear dependence on 1/v. So we can extrapolate the finite size data to the thermodynamic limit. In this way, we can estimate the value in the thermodynamic limit, and we study its gamma dependence. And then you find that it decays 0 as gamma decreases linearly. So this is consistent with our theoretical estimation of the relative entropy density. Okay, so yeah, anyway, since this vanishes as gamma decreases, so it means that the perturbation theory works in this model. Okay, next I consider the case of the boundary dissipation. Okay, so as a model, I consider the one-dimensional hardcore Boss-Hubbard model with the nearest neighbor and next nearest neighbor terms. So this model is known to be non-integrable and obeys ETH. And in this case, I consider the 4 Lindblad operators. Yeah, L1 and L2 act at the left edge of the system, okay, and L1 injects a particle from the left reservoir at the rate 1 plus mu, and L2 removes a particle from the system at the rate 1 minus mu, and L3 and L4 are defined in this way, act on, at the right edge of the system. So yeah, this is our model, and in this model, I calculate the relative entropy density. Oh, okay, so yeah, in this model, the gap delta scales as v to the minus 1.5. So this implies that our criterion cannot be satisfied for macroscopically large system. Okay, so this is a result of the relative entropy density. Okay, similarly, I consider the system size dependence of S and extrapolate the data to the thermodynamic limit and study its gamma dependence. Then you now find that it does not go to 0 as gamma decreases. So it means that the perturbation theory breaks down for arbitrary small gamma in the thermodynamic limit. So the steady state is not described by a Gibbs state in this case. So finally, I explain why the NESS is not described by a Gibbs state in the boundary dissipative system. So in our model, there is a diffusive transport from left to right in the steady state. So the diffusive transport implies that if we look at the particle number density profile, this kind of gradient appears. But because of the translational invariance of the system Hamiltonian, if we look at the single energy eigenstate, then the density profile should be flat. So in other words, this kind of inhomogeneous state cannot be reproduced by the classical mixture of the energy eigenstates in this way. So this is the reason why the NESS is not described by the Gibbs state in the boundary dissipated system. Okay, so this is the summary of my talk. So yeah, I consider the NESS over a macroscopic open system in the weak dissipation regime. So I take the limit of gamma going to 0 after the thermodynamic limit. Then I find that NESS is described by a Gibbs state if the system Hamiltonian obeys ETH and weak dissipation perturbation theory is valid. But okay, this is not so trivial. So I derive a criterion for the validity of the perturbation theory here. And this criterion implies that when for the bulk dissipation, the NESS is described by a Gibbs state, while in the boundary dissipated case, NESS is not necessarily described by the Gibbs state due to the diffusive transport. Okay, that's all. Thank you very much.
Okay, so are there any questions or comments? Yeah.
I guess you have transport even in the first, because you have electric field or light.
Okay, boundary, this one.
But paths.
Bar case, okay.
Can you go a little earlier, like the first model where?
First model. Okay. Okay.
So electric field or the bias due to light.
Bias, this one. Sorry.
Psi or cos.
Okay, yes.
Yeah. Transport here also. Transport of energy.
Yeah, this model is rather special because this time dependence can be eliminated by moving to the rotating frame. So maybe this is a special case.
Then you have electric field.
Oh, but in this case, we consider the translation invariant Hamiltonian and the dissipation. So if we start from the, for example, the translation invariant initial state, then there is no transport.
No, I'm asking. Estimation for that time dependent part.
Hmm?
It just Hamiltonian do you get?
In the rotating frame, we have this one.
You get just some kind of shifted energy.
Yeah, yes.
It's possible that actually the steady state is given by maybe local Gibbs state. Then the
Yeah, there's such a possibility, but I have not investigated. But yeah, in order to test this conjecture, maybe the larger system size is necessary. It's very hard.
because if you like if you take an integrable model so that it's ballistic, then do you get then of course you have a flat profile.
In some integrable, in integrable systems, we have the generalized eigenstate summarization instead of the usual eigenstate summarization hypothesis. And if we combine the generalized ETH and the perturbation theory, then it is concluded that the steady state is described by the generalized Gibbs ensemble. And the point is that the system Hamiltonian is integrable, but the dissipation breaks the integrability. But even in this case, the steady state is described by the GG. And I confirmed that, numerically confirmed that the perturbation theory even works in this case.
Right. So ask that you answer that you information is all itself is says
Okay. Actually, in the sense that the relative entropy density goes to 0. So it means that the steady state is very close to the deep state. Yes, yes. And there's an argument. If we consider the, for example, off-diagonal ETH, then it is very natural that the diagonal element of the density matrix is a smooth function of the energy. If we believe it, then by using some kind of large deviation principle, we can conclude that it is actually very close to the Gibbs state. We consider this small energy window. Okay.
Sorry, I'm maybe confused with the notation. So you had an effective temperature.
Yes.
And that you call as 1 over beta, right?
Sorry?
What do you call it as 1 over beta?
1 over beta.
1 over beta, right? So that should be related to zeta, right? Because the effective temperature is coming from, I guess, the strength of the drive, right?
Okay. Maybe. Depends.
So that inequality, strictly speaking, should be written in terms of Hamiltonian parameters. This way you don't even have to bother about the effective temperature. So how does the effective temperature scale with zeta?
Okay.
And what is this beta E is the temperature of the bath, right?
Yeah.
So if I switch off the drive, presumably do you go to the real temperature or is that limit non-trivial?
Yeah, non-trivial. So beta is different from beta E, and maybe beta depends on some parameters in the Hamiltonian or thing. So, but, okay, for this specific model, I have not investigated the dependence of beta on some parameters. Sorry.
Other questions or comments? Okay, so let's thank the speaker again.